All right, let's build on a number of forces that we can play with in solving physics problems. Today, namely thinking about friction and systems in general that end up being massless. But one example of where that pops up is tension. Let's take a box of mass m, and suppose you push on it with some force F such that there is some angle, you're pushing at it at an angle, and you push the box, but it does not budge. So you're pushing the box with some force F, which happens to be at an angle. If the box remains stationary, what forces are acting on the box? Now if I were to analyze this, my system is going to be the box. I'm going to establish my coordinate system to be aligned with the floor. I'll call that direction X. I'll call the vertical direction Y. Up it'll be positive, right it'll be positive. Looks like there's a force from the hand on the box. So on box from hand. And in this coordinate system, it looks like if I were to break into components, it looks like it's going to be positive, whatever my net force is, times cosine of this angle. And then the vertical component looks like it's going to be pointing in the negative direction, the overall magnitude times the sine of the angle. There's gravity. So gravity on box from Earth's gravity, this coordinate system. Since I said up is positive, it might be something like negative mg in the y direction. And that's also touching the floor. So I expect there to be a F floor component on box from floor, which might have a component that is parallel to the floor and a component that is perpendicular to the floor. The perpendicular one, you might call it the normal force, if you want to say that. If nothing's moving, that means velocity is started zero and stays zero, then that means there cannot be any acceleration, so there can't be any net force. So if I add up all these vectors, I better get a zero vector. Particularly in the x direction, the sum of the x components better add up to zero. And notice that implies that there's the force from the hand there's no component from gravity. And notice if I did not give a horizontal component to the floor, it would be impossible to have the box not accelerate in the horizontal direction because the force I just wrote down would be the only force, which has to be equal to m times the horizontal acceleration. If I want this thing to add up to zero, there has to be a second term here that cancels out the first term. Namely, in this case, it allows us to say that the floor better have a horizontal force component that is equal in magnitude and opposite in direction, not because of Newton's third law, but because of Newton's second law, so to balance out the force from the hand. This horizontal component is friction. A component, if you have a surface that you are in contact with, there can be a perpendicular component, the component that points perpendicular away from the surface, call it normal force. And if there's a horizontal component, that is the friction component. In this case, this is an example of static friction. Static, and that in contrast to kinetic friction, where there is a friction component, but there is relative motion between the object you're studying and the surface. Static friction, more or less, it aims to maintain zero relative velocity. That is nice. Yeah. Zero relative velocity between the surface and your system. So you can imagine, sometimes it can be tricky to determine which direction the friction component should point as a vector. You can imagine, let's take the example of, say, a box to remove the agent of the hand. Let's just have a box on a ramp, but it remains stationary. There's something about the ramp that's sticky enough, or there's enough friction such that the box does not move. Again, we could think geometrically first. There's a vector pointing down that's on box from gravity. And that's also touching the ramp, so there better be a vector from the ramp as well. And I can immediately write down what that vector has to be. It has to be exactly the same vector, as gravity, but opposite in direction. Because again, vectorially, when I add these up, I better get 0, because there's no acceleration happening on the box. So in this case, the ramp has a force that, in this particular example, is pointing straight up on box from ramp, relative to the ramp itself. And so if I break it up into components, there is a component of this force that is perpendicular to the ramp. This was an arrow. And then there's a component, in this case, that is parallel to the ramp. And it's pointing upward in this case. And this one's pretty easy to imagine, kind of that the friction component should be pointing up the ramp. In general, what you can do is you can imagine the system imagine the situation if there were no friction, and determine what the resulting acceleration and ultimately what the velocity of the object would become if there were no friction. And then you can reintroduce the vector component of friction such that it cancels out that relative motion. So in these cases, with both static and kinetic friction, where I might imagine I could take the box and imagine it starting at that location. I could paint the part of the ramp where it's starting blue. If there were no friction, then if this is where the paint was, if there were no friction, then a microsecond later, the box might find itself there and would have moved down the ramp a little bit. Friction wants to remove that relative motion. Essentially, it wants to keep the box where the blue paint was drawn. You could imagine friction wants to if you want to imagine motion, which is a little imprecise, you can imagine that it wants to return the box back to where it started. In this case of static friction, the box never moved at all. It wants to keep it hovering above where I drew that blue paint. So in this case, since the box wants to move down the ramp if there were no friction, friction better counteract that desired motion and point that way. Similarly, if there's, say, kinetic friction, right, I could have, suppose I have two boxes and I yank out the bottom box. So I grab just the bottom box and pull the bottom box forward in this case. If there's friction, static or not, between the two boxes, which way should the friction component point? Well, in this case, if there's friction, let's take the case where there is no motion. Let's see if I can come up with an example here. Let me go back to my book, and here's an iPod case. Where I can imagine if I'm pulling the box to the, or if I'm pulling the book in this case to the right, notice the iPod case is, or AirPod case is moving with it. Though I'm not touching the case, there is no horizontal force that I am applying to the iPod, or AirPods in this case. Something, though, must be applying a horizontal force to the case, else it would not accelerate in any direction. If there were no horizontal forces, I have to cheat a little bit, then as I pulled the book, nothing would happen to the case. But since it seems to be moving with it, there is a horizontal force being applied to the case. That's friction. Friction in this case is helping the case move along with the book. So again, you can imagine painting where the case or the book or whatever it is started. Then you can imagine the location if there were no friction, a microsecond later. And if you were to just pull on the bottom book and there was no friction component between them, then there's no reason for that top book to move at all. So it would stay perfectly stationary while the bottom book or bottom object moved to the right. Friction wants to eliminate that relative motion and wants to bring the thing back to being directly above my paint. So friction better point in the right direction in this particular case. Friction is what makes the top object move to the right. Friction usually friction is trying to slow things down. We could be more precise and say that friction wants to eliminate relative motion. Kinetic and static friction want to eliminate relative motion. Now, to come up with the magnitude of the friction term, that involves some modeling of what we think actually is going on at the microscopic level for friction. So friction is ultimately an electromagnetic interaction where molecules between the two surfaces that are in contact actually do exchange some electrons, and some bonds might form and then break, and those microscopic interactions are what cause that kind of rough interaction between them. That's what ultimately, in the case of maybe having relative motion, slows down that relative motion or reduces that relative motion. And you can do experiments where you can see that there are cases where if there is friction between this book and the case, I can slowly increase the tilt and the case is not moving. Though I imagine the more and more closer it gets to vertical, the more friction has to do to resist gravity from making the thing slide down. And eventually it does slide down. So static friction is one of these passive forces that I talked about before, where it can adjust its value to be what it needs. So that the relative motion between the two objects remains zero. Though, as we saw with the example I just showed, there is a limit until it eventually fails. And so if we want to try to model that or parameterize that, the idea is that we think it has to do with the perpendicular component as well, because the perpendicular component is the geometric constraint that keeps this thing from falling through the book. And it's also kind of a measure of how much the object is kind of in contact with the object. And this has some sort of normal component. If I push down on the thing, then the book has to respond with a larger normal component to push back up to keep it from going through the book. If If I gently pull up on it but have it still be in contact, the book doesn't have to push up as hard to keep it from falling through the book because my hand is kind of helping to balance things out. And if in the case of it loses contact with the surface, in that case then the normal component goes to 0, and which is always a good test. If you're doing a calculation and you have a normal component that vanishes or becomes, or changes sign, that actually is saying that it's lost contact, the object has lost contact with that surface. And then you have to go back and redo the calculation from that point, assuming that there is no normal component. So if I take the force on the surface to be a friction component, and I'll use the term normal, right, as a normal component where this is the parallel component to the surface and perpendicular to the surface. So again, I'm writing these as coordinates. It doesn't have to necessarily be xy, but the part that's parallel and the part that's perpendicular. You can rotate your axes so that that's the case. Static friction can only go up to some value, and that's going to depend on the surface. So we can have these mu values, mu sub s, a friction parameter that tells you more or less how strong, how sticky the surface is, for example. And it also we model it as relying on how much the object is in contact with the surface, so the normal component. So we use that to parameterize static friction. It can be any value between 0 all the way up to this quantity here, whatever it is. And you can look up values of mu's and books and stuff like that. Multiply by whatever the normal component is at that location. That gives you a sense of how much how much friction can do before things start to budge. If the forces that are trying to make the thing move exceed this friction force, then the thing starts to move. And then you get kinetic friction, where there is a constant relative motion. So there is rubbing going on between the two surfaces, but the friction is acting to eliminate that relative motion if it can. This is a more active force in that when you do experiments and you measure the amount of interaction that's going on between the two surfaces, you notice that once it hits the static limit, the amount of friction force that is being experienced kind of drops down and kind of hovers around a roughly static value. So then there's another kind of parameter component, a mu for kinetic friction, multiplied by whatever the normal component is at that location. So there, it's not any value between 0 and mu sub s times n, but it just becomes a constant value, mu sub k times n. And that's friction. Acting to eliminate relative motion. So good things to remind ourselves of. So an example might be, it's probably one you've done before. Actually, no, that's a pretty simple example. Let me do one where, suppose I have 2 books, and it's on a table, and we haven't done ropes yet, but suppose I attach a rope to the top box and I pull on the top box, and the surfaces between the 2 boxes are rough. What forces do I expect to act on both boxes? Well, the top box, I expect there to be kind of force from the rope, probably pulling to the right in this case. There's gravity, which I expect on top from gravity. That's going to be pointing down. And then I could do my experiment where I could paint this part of the box blue. And imagine that if that was it, I guess, and it's touching the bottom box, so there's at least a normal component, but maybe there's not friction. Knowing that the surfaces are rough, I say, okay, if I want to introduce friction in, should friction point to the right or to the left for the top box? In this case, again, I can do the experiment. I can paint the part of the bottom box blue, and if there was no friction component, I can imagine what direction the box would accelerate by just the forces I've written down alone. In that case, it looks like it wants to accelerate to the right, if I look at the horizontal components for these two vectors. So the top box wants to move to the right relative to the position on the bottom box, so the friction component on the top box better point to the left. So in this case, there is the third component of on top from bottom, which is going to have a normal component that points up and then a friction component that points left, so it might have a vector that points something like this as a result. And then when you break it up into components, right, that might be a left horizontal and an upward vertical. Now if I were to do the bottom box, let's suppose it's sitting on ice, though I could also think about the interaction between the floor and this box too. Well, it's not touching the rope, so there's no rope force. There's a gravitational force that we have to consider. There is the floor, so on bottom from floor. If it's ice, say, it's going to have a normal component but no friction component, so it's going to point up. And then there is the force of on bottom from top, because was it touching? Again, I don't want to think of friction and normal forces as their own unique thing. It's that they are parts of what is the real force on bottom from top, the fact that the two boxes are touching. But that is the Newton third law pair of on top from bottom. So if in the red I said that on top from bottom points diagonally up to the left, this is going to be a vector that points diagonally down and to the right in this case. And if I figure out what the components are for the top box, I can just throw minus signs in front of both of them, and then I know exactly what that bottom should be. So in this case, again, since that interaction included a friction component, friction is what is making the bottom box accelerate to the right in this case. It is the only thing, as you can see, that has a horizontal component. So if the bottom box moves horizontally, it, in this case, was because of the friction interaction between the two boxes. All right, tension. Or more generally, massless systems. Often you have to deal with massless objects. Now, it's a bit of a abstraction, right? Because really nothing is really massless. But often there are cases where you might have objects where the mass of one particular object is exceptionally small compared to other objects in the system. Rope is usually good examples that we talk about where we treat them as massless systems. Right, in that case, it might be there's a rope holding together two boxes, and maybe the boxes themselves are, pounds of weight, where you have a very thin rope attaching them that is essentially not changing the total mass of the entire system, and can be relatively well approximated as just being massless. Pulleys are kind of another example. If the pulley has all of its mass more or less concentrated in the exact center, then if treating it as massless doesn't really introduce any huge amounts of error, because then you don't have to deal with the rotational dynamics of the pulley. Let's look in the case of what this implies for the tension along a rope if you allow it to be massless. Suppose here's the wall and there's a hook which is knotted to a piece of rope which you pull taut with your hand. So you're pulling on the rope, some force to the right. And that's causing the rope to stiffen up. We could ask ourselves what's going on inside the rope, and then what's going on where the rope meets your hand and where the rope meets the hook. Now in this case, we expect at least there to be a component that is kind of along parallel to the rope. That is kind of what's holding it rigid in this sense. We call that tension, right? That there's tension along the path of the rope, or along the path of, if you were to imagine the rope, in this case, as a line. If we want to analyze what's going on, we could do a force analysis of, say, a little tiny piece of rope. So I can imagine making this little tiny piece of rope my system. And I could even give it a little bit of mass, right? Maybe it's a uniform rope, so the mass is kind of uniformly distributed along the rope. So there might be a little dm. I'm going to write as a dm because I anticipate this. I'm going to ultimately consider this in the limit where it goes to 0. But again, you can imagine this with an actual rope that has mass, but just zooming in more and more and more and more to a tinier and tinier little piece of the rope. Well, in this case, I could ask what is touching my system, the stuff that's in the red box. Well, it's touching this part of the rope here, so I expect that maybe there's a force on my system from the right side. It's also touching the rope right here, so I expect there to be a force on my little system from the left side in this case. Let's just focus on horizontal motion for right now. In this case, it looks like if I were to do a force, Newton's second law, and I take to the right as being the positive direction, it looks like then it's saying that the force on the right side of my system minus the force on my left side of the system is equal to the mass of my system times the, in this case, horizontal acceleration. Or that the acceleration that little piece of rope experiences seems to be delta F over dm. Now if I'm just holding the rope, I should have brought a rope, because we'll use this, right? If I'm holding the rope and it's stationary, well, stationary means there's no acceleration, velocity is 0 and is staying 0. So in this case, if it's stationary, then A is 0, which implies that tension force that's emerging on the right side of my system is the same as the tension that's arising on the right side of my little system. That's kind of straightforward. And then I did that for one tiny little piece of the rope. You could imagine then scooting over a tiny little nudge, doing the same thing. You'll get the tensions are going to be the same. Scooting over, tensions are going to be the same. And you could imagine doing this for the entire rope up to when it starts touching something else, like your hand or the hook. So you can imagine that the tension is something that is uniformly established throughout. But I claim that even if their thing wasn't stationary, if we take the rope to be massless, F net must still be 0. Right? Notice by saying that these two are equal, right? That's the same thing as saying that F net, which is the difference of the two, was 0. But as you let dm go to 0, so now we're going to think kind of calculus-wise. As dm goes to 0 and that thing gets smaller and smaller and smaller, notice what's happening to the acceleration. You can imagine that there's some difference of forces, and maybe they're uniform, maybe they're not, if the thing, as we let dm go to 0. But as dm goes to 0, that thing's in the denominator of this expression. So if the numerator is non-zero, as dm goes to 0, you got a problem. Because as dm goes to 0, if f net happens to not be identically 0 also, then A explodes. Or I might say that A diverges. You essentially have a divide by 0 issue. Dividing by 0, frowned upon in nature. So we can actually make a statement that if your system is massless, then you must require that f net is 0. On your system. Else, you have this issue of your acceleration that you calculate for your system requires you to divide by 0. And again, it's a bit of a trick because nothing is really actually massless. But you can also convince yourself that this has to be the case, where if you don't want it to be massless, you can do the calculation where you can let it have a tiny little mass dm, solve for your resulting equations of motion, and then take the limit of letting that little dm go to 0. Ultimately, you arrive at, you must require, for systems that are massless, there cannot be a net force on that system, regardless of what it's doing, stationary or not. And so for rope, this establishes that the tension established in the rope is uniform throughout the segment between the two locations where it's being taut. In this case of the apple, the part that's kind of hanging vertically and is attached to the apple is taut. The endpoints being my finger and the apple. Gravity is kind of what's helping establish, right, the stiffness of the rope. There's tension there. I'm pulling on the horizontal part so that it is also stiff. In this case, there is also tension in that part, which might be different than the vertical part. But then this dangly bit we can approximate that as not having any tension at all. There's no second endpoint that is keeping this held stiff. Now again, for an actual rope that has mass, its own weight is what holds it down and keeps it stiff. In that case, the tension can change throughout the segment. That's a more complicated problem. If you keep the thing massless, then that establishes that there should be a tension throughout and that it's the same throughout. And then that tension can be applied to other objects that it is attached to, namely whatever is going on at the endpoints of the rope. And we could go back up to our example, our drawing here, and imagine having my system now be the little part, let's go up, the little part here, right where the rope comes in contact with my hand. In that case, the force analysis would give me something like that there is a force from the hand on that little segment, and then there's what I'll now start calling T, some sort of tension force that is pointing to the right. And since that little segment of rope is massless, the net force must be 0, so that we can then say that the tension is established by the force from the hand in this case. Similarly, if I go to the hook and then analyze the piece of rope that just finally comes in contact with the hook, there is going to be the tension component going along the rope, and then there's going to be some force from the hook, which also starts with an H. I'll write out hook. In this case, knowing the tension is the same as the force from the hand, this also shows that the force that the hook is feeling on hook from rope is also going to be the tension, same as the tension. So in general, let's see, what can we highlight? In general, for massless systems, you must require there be no net force on that system. I think that's a good trick to remember with cases where you have something you can approximate as massless. Let's do one example and then call it a day. Let's imagine that there is a platform of mass big M, and it is attached via a rod to a pulley. That pulley then has a rope that is attached to the ceiling, and you are pulling on the other end of the rope. You have mass little m. We're going to take the pulley and the rope as massless. You pull up on the rope with some force F. What force do you need to exert so that you and the platform accelerate upward? So ultimately, you and the platform are moving together with some acceleration A. You have mass, the platform has mass. Pulley and the rope do not. How can you figure out what force you need to exert for this to happen? Now in this case, there are a couple ways you can solve this. It usually is, for any physics problem. You can do this by kind of tackling individual components, treating individual components as your systems, identifying Newton's third law pairs, as well as identifying commonalities that certain systems share with one another. For example, you and the platform better have the same acceleration if you're moving together, else you would start to move relative to one another, which doesn't really make sense. Knowing that the pulley and the rope is massless, maybe you could also define systems that don't have any mass, in which case you could use the requirement that the net force on that system better be zero. So let's take a couple systems one at a time. Let's first do a system that is just the piece of rope that comes in contact with your hand. So at the place where the rope comes in contact with the hand, also notice this entire problem is vertical. I'll write things as vectors to start, but all this motion is vertical as well. At the part where the rope touches the hand, I expect there to be a force of on hand. Let's see. Well, I'm studying the piece of rope that's coming in contact with my hand. So there's on rope from hand. And then I might expect a force of just the tension in the rope. All right, on that little piece of rope from the rest of the rope. Which if you go up to the previous example, we're going to be able to approximate as this tension is going to be uniform throughout. Since this is a massless system, this better equal zero, so I don't have to possibly have infinite accelerations. In this case, the rope does have some acceleration, right? As if you look at little pieces of rope as you're moving around. But again, we have to require that the net force is zero, else Newton's second law claims that the acceleration is infinite. So assuming that I'm pulling up on the rope, and I take up to be the positive direction, I might say that this is F hand in the vertical direction. Then there is some tension in the rope as a result, and that better add up to zero. So in this case, it looks like the tension in that case is same in magnitude as the force exerted by my hand, but in the opposite direction for that little piece of rope. So in this case, we can say that T is uniform throughout the rope. And for other systems, the directionality of that tension will be, pointing away from the little system that I've drawn. So more or less, if we can find the tension in the rope, I can then calculate what the force I need to exert in order to have this acceleration occur. All right, let's look at, and then I can do the same for the rod, of course. The rod will have its own tension. It will not be the same tension, but there will be some tension in the rod that is connecting the pulley to the platform. So now let's do some force analysis for various systems in the problem. Let's start with the platform. For the platform, it looks like there's a gravitational force because it has mass, so it would be kind of on platform from gravity. I expect that to point downward. So underneath I might dispose of the vectors and call that negative mg. And then I can ask, what is it touching? It's touching the rod, so I expect there to be a force on platform from rod. Then it is also touching me, so then I expect a force on platform from me. And if I look around, I don't see it touching anything else. It's not touching the pulley, it's not touching the ceiling, it's not touching the other rope. This then better be equal to capital M times the resulting acceleration, which, to get rid of the vectors, we're just going to write as M times A. The platform, on platform from rod, well, again, I can think of that as a tension that is pointing away from my system. And maybe I'll call that not just T, but T sub R for T rod, say. And then there's on platform from me. I'm going to come back to that because we need to think a little bit more about what that is. All right, new system. How about me? In this case, I have some mass, so I expect on me from gravity, which again I expect to be negative little mg. I am touching the rope. And we've just talked about how I'm exerting a force, F hand we called it, on the rope. Therefore, of course, the rope exerts a force on me. So in that case, I might write this as plus force on me from rope. I am also touching the platform. So I expect there to be a force on me from platform. I'm not touching anything else. Looks like we're done. And that better equal my mass times the acceleration, which again I'll write as little m a. Not giving little a sign, notice, right? I just left it as positive a, which could either mean if a itself is positive, that means up. I could also, if I let a have a negative value, that could also mean what do I have to do in order to make the thing accelerate downward. Though in this case, you can imagine, just like gravity do that. Now, on me from platform in the vertical direction, well, that just sounds like the normal component pushing up, that the platform is pushing up on me. So I might call that n if you want to use, positive n if you want to use that as signifying the normal component, the contact force between the platform and my feet. But then we can go back up to the platform and look, on platform from me, that sounds like a Newton third law to on me from platform. And indeed, it is. So this better be negative n in that case. I'm exerting a force on the platform as well as the platform exerting a force on me. And then there's on me from rope. And we said that I'm pulling up on the rope with a force F hand, and that created a tension in the rope T. So then on me from rope, that's the Newton's third law counterpart. The rope is exerting a force on my hand as a result. All right. We could stop and ask, is this enough? Can I uniquely solve this situation? You could ask yourselves, I essentially have two equations. I have the platform equation where I know big M, I know little g. I don't know this tension in the rod. I don't know this normal force. I know big M, I know A. A is going to be taken as a given. Then the second equation, I know little m, I know g. I don't know the tension. I don't know the normal component. I know little m, I know A. So I only have two equations, but I have three unknowns. N, the tension in the rope, and the tension in the rod. So we're not quite done yet. We need at least one more equation that can hopefully disentangle this. So I might use, maybe I'll use the pulley as my third system. And it's getting a little busy up here, so maybe let me redraw it down here. So I have the pulley, then there's the rope that's coming on both sides of the pulley, and then there's the rod. And I'm having that be my system. Not rod, pulley. Well, in this case, it's massless, so we don't have to worry about gravity. But it looks like there is a force, let's see, so force on pulley from rod, and then there is twice the force on pulley from rope, because the rope is touching that box I drew at two locations, so the force has to appear twice. And I expect them to be both pointing in the same direction, which is why I wrote 2 times the 1 vector F pull on rope. This is a massless system, so these things better be equal to 0 when I add them together, or the net better be 0. Now, on pulley from rod, if you think about it, the platform established a tension in the rod. We call that T sub r, T-rod. That is uniform throughout the rod, so then that is also the force that is exerted on the pulley from the rod. We expect it to be pulling downward in this case, so I expect this to be negative T-rod, tension of the rod. Plus, similarly, this then is twice the tension in the rope, what we call just T. And that equals 0. Ugh. And notice in that case, before my screen vanished, that gave us a third equation involving the 3 variables we did not know, which was T-rod, T of the rope, and then the normal component between me and the platform. So we are off and running. We have 3 equations and 3 unknowns that we can then solve. Essentially, we want to solve, let me just highlight rather than recopy. We want to solve this, this, and this for the 3 variables we don't know. And I'm not going to bother going through the math for that, but if I label this as equation 1, if I label the platform as equation 2 and me as equation 3, then equation 1 implies that the tension in the rod better be twice the tension in the rope. And then if I combine the second and the third expressions by adding them together, And why might I want to do that? Well, notice in both those cases, there's a normal component n, but one is a negative sign, one is a positive sign. So if I add them together, the n will cancel out. So notice if I add them together, I get something like that the tension in the rope minus, and then the gravities add together, sum of the masses times g, that then is equal to the sum of the masses times a, since they both have the same acceleration. Well, this is great because there's now an equation that only has one unknown. So then I can conclude the tension in the rope, similarly the tension that you have to pull on is, when I combine these two and move the gravity components to the other side, looks like it is just, the tension is the sum of the masses times the sum of the two accelerations, gravity and the acceleration upward that I have. That then, if I go back to the first equation, says that the tension in the rope is twice this. So then if I have two of my unknowns, I can pick my favorite equation above that and solve for n. So I might then say that from equation 2, I can say that the normal component then looks like it's going to be the tension in the rod minus the big mass times a plus g, with a little rearranging. So then that looks like it's something like, notice that this is they kind of are similar to one another, because this is 2 sum of the masses times a plus g minus only big M, a plus g. So it looks like if you multiply the 2 in, one of the big M's cancel. So this looks like it's going to be 2 little m plus big M, a plus g, as a result, is my normal force. And so that would tell us, maybe highlight those as well, right? The normal component, the rod, and the string. And again, it's by cleverly picking systems where you can do force analysis. In this case, I included as well the pulley as one of those systems, which then gave me enough equations to figure this out. All right, more problems to be done in class, of course.